Okay, so hello again. Last time, already we were talking about neural networks and an introduction to deep learning. We went through a brainstorming when we were asking what does deep learning means for you and collecting the different answers. We tried to create different groups. Most of the answers fit in the group of definition, basic knowledge about neural networks and deep learning. Other groups much more in the category of architectures and, for example, layers, things related to the architectures, MLP, or things like this. And the other group mainly focused on application or domains particular applications of deep learning in the real life. So from here started our journey. We said that, okay, there may be particular specific course for deep learning, which may dive more in details than the AI class because we might not have enough time, but I will do my best so we cover many things. Okay, so we started with the basic knowledge and we said that how it's coming, the idea of a neuron. It's in the start inspired by the human or from the human biology. And we say that in biology, there is already the neuron. It works like it has dendrites, it has a cell body, it has an axon. These are the main components. What we did is that trying to assimilate this in order to create a model. And this model is the first artificial neuron. It's just a modelization of the existing biological neuron, which takes inputs. So this one also takes inputs. We denote it with X. And each input has a given importance or intensity. It's the weight W of that input. And at the end, there is a function which computes the sum of products of these inputs, which is the aggregation, which means we are each time multiplying each input X with its importance or weights, summing all that, so we have the output Y, which says whether or not this function is activated. So if, for example, the value of Y, the function f is giving a positive result, which is more than 0, let's say, then Y is equal to 1, which is activated. Otherwise, Y is equal to 0 means there is no reaction. Okay, we give it the example, if I'm touching something, it's that much hot, the sum of products, it's having a high value, means I'm going to take back my hands. But we are not at this level because this is just a modelization. There is no training, there is nothing. Just I have the function, it takes inputs, it computes, it gives outputs, and that is it. Then we say that in the reality, it's not like that. We have a connection of multiple neurons, and it's going to be like a connection of multiple functions, F, taking multiple inputs, X, Y, is coming from different layers, and we will dive into these details. So the first, the timeline starts after the first neurons, with the invention of the perceptron. And when we say perceptron, I was mentioning that we focus on the learning algorithm, okay? So a perceptron is if we are taking the same idea of the artificial neuron, but we are talking about learning, and we are now aware about the learning thing in AI, okay? Learning in machine learning and learning in deep learning. So learning means what? Means I know something which can help. There is an information that I know, and this can help. This information is based on the help theory. If I have two neurons which are jointly excited, then it's going to impact the next one, or it's going to strengthen the synaptic link. And this what happens, okay? This is what we discussed last time. And we said, if we are talking about learning, and this leads to the idea of the perceptron, which means that if I'm learning from training data, and the training data is supervised, which means that I know the actual Y value, the output value, and each time given this trained value, I'm computing F, I'm finding the output. If it's not exactly what I'm expecting, I'm going to update. I cannot update the training data So what I update is the connections or the weights, okay? W. So this is the idea of perceptron, and we were like discussing how it works. And next, one perceptron is not enough because in the reality, we have a connection of multiple perceptrons. So the idea is after like many years, there is in 1986, the multi-layer perceptron idea. So the multi-layer perceptron is coming first. So the idea of the multi-layer perceptron is coming because there are some problems in the literature. At that time, they were not able to solve. Mainly, so if we were discussing the first paper that is introducing this idea, I'm going to come back to this paper. So in this paper, we say that with this, like we can solve problems like and or, for example. However, you know the XOR problem, and we went in the AI class through the truth table. So with the XOR problem, it's a different problem. So we cannot solve with only one perceptron. So what we need is to move for like another model. The idea is like, for example, if I have these two like sets, I have this data, the red one and the blue one, I can divide this space or create this linear function in order to divide this like space. This problem is linear because it's very easy to make a separation only using this line. And we know that this line has as equation, f of x is equal to ax plus b. So what we have here, the a and x, and for each one, we have these parameters or weights is what we can edit, okay? So we can edit the value of b, which is going to change the origin of this like line. And we can also train the weights, which is the importance of each input, okay? These are the inputs, red and blue plots, okay? This one, they are corresponding to the class 1, and these ones, they are corresponding to the class 0, okay? So what we have now, if we have a problem like this, when a linear function is not enough to separate both like classes. So in this problem, a linear model is not enough, no matter how like the combination of parameters you can use, you won't be able to find a linear like separation between both classes. So this just highlights the limitations of the linear neuron and shows that, okay, even it's easy to compute, and even in this model, it's very simple and there is no hidden layers. There is a problem, which is it cannot deal with the complex like situations like the XOR one that I'm mentioning. XOR problem needs, let's say, a more advanced or complicated model, which is the multi-layer perceptron. In the multi-layer perceptron, what you will have, you are going to have a connection of neurons, which are, we call them fully connected. And when I say fully connected, means we are not in the case of a graph when somehow you find that this neuron is only connected to these two. Every neuron from a layer L is connected to all the neurons from the previous layer. And this what means fully connected, okay? Is that clear? Okay, see this one also, for example, is connected to all the neurons from the previous layer. So this makes it possible to solve complex problems then using only one function. So what we are doing here, it's like we are having multiple functions. You see, connecting these functions, you can create like a nonlinear separation. So let me illustrate this example with like what we say. If I have my data, there is a way that these points I can separate from these points with this function, which is a linear function, okay? Perceptron is okay for this one, just one. So if me, I have my data somehow is like this, and then I have one like this, I cannot draw a line that is making the separation. So even if you might think of it, so you can do something like this, somehow it's a linear function, this only segment having a linear function. So when I'm saying something linear function, I'm talking about one neuron, okay? You can think of another one, which is another function, which brings to your brain another different neuron, okay? So this is how we can think, because if you zoom on then you can do something like this. So if I may zoom, like if I have a problem like this, and the separation is like this, so this is a non-linear function, okay? But if I will zoom, somehow I can find at some points there is linearity, okay? So I can make it different segments or different functions which are at the end linear, but the connection, or like if I'm going to put them together, it's non-linear, the whole curve, okay? So this is the main idea. What we will do now, that we are going to move from one function to multiple functions. We are in the case of multi-layer perceptron. So instead of having only one function, taking x's and weights and giving an output y, the output of this function is going to be given to another function. These x's could be given to another function, which is a neuron from the same layer, and so on, okay? So we start with a simple example of 3 neurons only, and we will see how it works. So for the first one, we know that it's going to take the input x's, their weights, and do the sum of product to give the output y, plus some variable somewhere. Okay, so we have w, what we say here, 1, 1, because we talk about the first layer. 1, 2 is for the second layer. So you might have the notation of WIG. Okay, so don't worry about that. Here, W11, the first one coming from X1, plus W21, the first one coming from X2, multiplied by X2, plus something. Okay? If what we have, the X value here is equal to 1, if this function is giving a positive value, otherwise, it's equal to 0. The same for this one, what we have, W21, what we see here, W11 is this one, W21 is different one, which is connecting the input X1, okay, to this neuron, second one. So it's a different weight than this one. This is why it's W21 and not W11, okay? This W21 multiplied by X1 added to W22, which is also different from W12, multiplied by X2 plus some value. Again, if this Y2 is equal to 1, then, which means translated only if the function is positive, otherwise it's 0. And at the end, this neuron is taking what? This is coming from the second layer, okay? Which is not straight connected to the inputs, okay? So here you forget about this layer. You only focus with this layer, okay? So the input for this function are the output of F1, okay? And the output of F2, okay? With some importance, because each one is going to have some weights, okay? On the connections. So this is why F3 is equal to W31, it's here, times W1 coming from the first function plus W32 multiplied by the output Y2 from the second function F2 and plus some value. Again, if this one is more than 0, so it's equal to 1, otherwise it's 0, okay? Is that clear? So if you might have like this case, you have 3 neurons, which means 3 functions, okay? Each one is having inputs and outputs, and the inputs are connected via weights and so on, okay? So the first layer here is having how many neurons? 2, and the second layer is having only 1 neuron, okay? So this Y3 is the output from this neuron, okay? Which is later going to be, now, if you have this kind of problem, so it allows you first to solve this type of XOR, like nonlinear problems, This is the first advantage. The second thing now, in this type of architectures, the last layer here, the layer 2, is having how many neurons? 1, okay? Which is corresponding to, so in this case, we have a binary classification. Binary classification, this neuron, if for example, Y3 is more than half probability value, then it belongs, for example, to the red, otherwise it belongs to the blue. So here, whenever you have binary classification, you have only one neuron in the last layer of your network. Now, it's just a multi-layered perceptron. However, we can have more functions. We can have more layers. So how many layers you can see here? So you see 1, 2, 3, 4 layers. So this is just the input layer. Okay, and this is the output layer. And you have 3 hidden layers, okay? All of them are fully connected. And now how it works? The same idea for F1, for example. How I'm going to compute this? I'm going to consider the weights coming from x1 multiplied by x1 plus the weights coming from x2 multiplied by x2. This is going to give me y, for example, 1. And then it's going to be used for F2, 4. And then the output of this one is going to be used for this one, and so on. So this way, I'm talking about the propagation of these results. They are going in one way. This is called the forward propagation, okay? So the forward propagation, also called forward pass, refers to the calculation and storage of the intermediate functions, these functions, including the output as well, for a neural network in order to compute from the input layer to the output layer. The whole process, how it's going to propagate in this way from the input layer to the output layer, is called a forward pass. If I'm going to go in the other direction, it's a different thing, okay? So this, now, once I'm going in this direction, which is the forward pass from the input to the output, I'm going to have a given value for my output, okay? It could be the expected one, and it could be not the expected one, okay? If it's not the expected one, what happens? What we are doing? There is a training process, which means I'm going to update all these weights and connections in order to converge to the desired output, okay? Because in the start, I know that this x1, x2 vector have this exact y. It's a supervised data set. So the weights are going to be updated now during the propagation. And how it's going to be? So the thing now, it consists of determining how the output of the neuron varies as function of the parameters W and B, okay, so bytes, present in each layer. Now, how it's going to be updated? I have at the end my computed value of y final, okay? And what I will use here, it is successive derivations, okay? The gradient, okay? So I am going, just this, try to learn it forever because it's a very simple trick, and don't get confused if you're having an interview or something. So you have the final one, you are going to go back. So you don't see anything before that. You see just the exactly before, okay? The exactly before this one is F4. So if you are going to have the back propagation, you are going to derive or compute the gradient with consideration to the one just before, which is F4. So you are going to have the gradient of y final, okay, given in consideration the F4. I'm going now to go back from F4 to the one just before. So what I do, I'm going to have the gradient of F4 with consideration to the layer just before, which is F3, and so on. If I'm going from the F3 to F2, so it's the gradient F3 given F2. And again, here, from F2, I am going to go back to F1. So like this, I am coming back using the gradient, And what I'm doing each time, I am updating the weights given the output, okay? So this is how it works. So we have a forward pass and backward pass. How I understand if what I'm doing, okay, I'm doing like propagation, backpropagation, propagation, backpropagation. How I understand if I need to stop or not, okay? My criteria is always that I need to minimize my error, and this is the optimization problem. So the error is what? Is I have my exact output, what I know, because my data is supervised. So I know the actual class, and I keep computing until this error is 0, or let's say minimized, because maybe it's almost 0, okay? So this is the idea. Thanks to the gradients, we can then update the parameters connecting the different layers, which are W and B, of each layer, so that we minimize the error between the output of the model and the expected response, okay? Next, so here, I don't know if you have any background about gradients or not, but one famous, one is the gradient descent, which is an optimization algorithm. And this one is used when we are training whether machine learning or deep learning model. And it's based on convex function. And when we talk about convex function, it's not like, it's different from linear one, okay? And it tweaks its parameters iteratively to minimize given function to its local minimum. So it's just a technique in order to have the final minimum value, okay? An optimization technique. An example is this one. If starting with the, because we will see that you will say how the weights of the network are initialized. This is a very important question. This X, okay, having the X1, X2, the inputs, I know that very well because it belongs to my training data or test data. The Y is also the class that I really know from the start. But who knows what are these connections, W? How they are initialized in the neural networks. These W's are initialized randomly, okay? So this is a problem. This is why, if you paid your attention here, there is a starting point. No one is asking why it's exactly starting from here. And there is no answer. It could start from here, it could start from here. It depends with the initialization. If you are lucky, maybe you're starting from the, but it don't happen. I never seen in all cases. So the thing is that these weights are randomly initialized, and we keep optimizing this function until like we are coming to the minimum point. Okay, how it works, this optimization technique? I always give the example of like, for example, I have this pen. I don't know if it's clear in the camera, or you have a stone or something, okay? And you throw it. Okay, you are someone who says, I want to go, okay, and put my legs exactly, I want to press there, okay, to stand there, exactly on that red point. So imagine I'm coming from the other classroom or from my house. So I'm far, so it's very normal that I'm running. I don't care, I'm still not there, okay? I'm near now to the point. If I will keep like it like fast, or I may miss this point because like this, I cannot be in the minimum point. And this is the problem of optimization technique. So I keep coming back and so on. So the idea is that the more I'm near to this point, the more I might be careful and I reduce my steps so that when I press, it's exactly in the minimum point. Okay, so this is the idea of the optimization, is that whenever you are reaching to the minimum point, you need to be really careful. Here you find different techniques, different functions, and different ways to approach this, okay? And this is an optimization technique or problem, is what to do exactly to reach to that point, for sure with less steps, because every steps costs me energy. Every like steps also costs time. So we always need to be careful about things like energy and steps, okay? Gradient descent gradient is just an example, but there are multiple like other examples. In summary now, you might like have focus on optimization techniques itself. It could be a different course, but the idea is this, okay? So the main, like in summary, or the main idea is how a neural network works. And this is what we need to learn. So a neural network works like it's a 4-step algorithm as well. And the first step is a forward propagation, which means I'm going from the input layer to the output layer. Then reaching in the like output layer. Here I would take my decision. Am I going to go back, or it's enough, I'm going to stop? And there is a stopping criteria. This is how I'm going to evaluate my cost function. So here there is like the idea I'm going to check and compare, for example, my predicted y with my current one. And if it's the same, then it's okay. If not, then I'm going to go back and apply the backpropagation. While applying like backpropagation, we could use the gradient descent, okay? So this is very simple, but if we are talking about this, we only talk about like the linearity. Until now, we didn't see any non-linearity. So there is something which makes neural networks non-linear, because whenever you listen about neural networks, you listen that they have the non-linearity. From where is coming this non-linearity? It's coming from what we call activation functions. We have like each function now, it has like a different way if I'm going to activate or not. There are multiple activation functions in the literature, but mainly the non-linear like famous ones, we have the sigmoid, we have the tan neurons, and we have the ReLU neuron. Each one is having a different, like you can see, curve. Like what we say if f is less than 0, then like there is no activation. If it's more than, like it's equal to 1, for example, if it's more than 0 for this part, if it's positive or it's negative, okay? 1 is equal to 0 and 1 is equal to 1 in this side. So it's not as simple as this, because sometimes we can move, or the transition from the 0 to the 1 could be like this. It's having this particular formula, 1 divided by 1 plus exponential minus z, which is called sigmoid function. Sometimes the transition here is not exactly 0, it could be negative, and then goes to 0, and then we reach to 1, okay? And this function, it's a hyperbolic tangent, okay, of z. And then you have the ReLU function, which is very simple. If you have here, it's 0, otherwise you are going to take the maximum between the values, okay? Now to keep in mind, it's very simple. When you talk about activation function, it's okay. If you are negative, go to the next layer, there is no problem. Really, no, if not, no, stop. Don't go anywhere, okay? So this is an illustration of the ReLU function, and I encourage following such like posts. They are at the same time funny and they illustrate things. So now we are understanding the whole concept, how it works, propagation, error evaluation, backpropagation, gradient descent. There is a non-linearity coming from the like activation functions. What now we will focus on is some particular like architectures, such as the most famous one, the convolutional neural networks, introduced in 1990. Okay, so CNNs are like mainly the work of the second group. There are other architectures that we may not focus much, but you might focus on advanced deep learning classes or deep learning classes. So like recurrent neural networks that came after like CNNs, and here like always there is some limitations in one architecture, and we are like trying to fix. It's always like this. So recurrent neural networks such as LSTM, also addressing different types of problems. And then there is here a very famous event, which is the ImageNet competition. I think last time I told you about this, which is like giving, let's say, birth again to the deep learning and to employing such architectures and so on. Recently, we talked about the GANs and Also the ChatGPT, which is revolutionizing everything right now. Now, in the start, we started motivating this lecture with different use cases and applications of neural networks, if you remember, or deep learning. So we, in the start, said that it could be useful for voice assistant, music generation, ChatGPT, and all. So this is using RNNs. It's a particular architecture. Things related to classification, object detection, and so on, it's CNN tasks. So for example, if you are reading a paper, this paper is employing CNNs, mainly is going to deal with some classification task, okay? Dimensionality reduction and compression and so on, it's encoder, decoder, or autoencoder architecture. And the rest of these like are generating things related to generating images, 3D objects, and so on. It's GANs. Multiple frameworks we discussed last time, and so we are done with the first part, which is neural networks. Any questions until here? Okay, now I'm going to dive very quickly into the convolutional neural networks, which is like very important for the third group. However, first and second group also might need to pay attention because both of them are like requested to use classification with a CNN, okay? And then we'll discuss the difference between both projects. So in the start, if we are dealing or with a typical classification like task, let's talk about the ML project now. The ML project, we seen that the first like task was just to check your data, okay? Upload, like read data, visualize, analyze. If you have problems with the balanced or such problems, try to solve, balance your data, whatever, okay? Next, before feeding the data to the ML algorithm, it's not possible to give the input to ML algorithm because in general, you have dimensions, the dimensions of the images are that much high. Don't consider the MNIST case, it's a little one, but they're also working with the skin cancer case. You have like large images, okay? So you cannot feed it straight to the ML algorithm, so the input size is that much. You need to extract some features. So you extract the features, you are going to do that using SIFT, but there are multiple techniques. So extracting features is called some engineering tasks. And if you remember the difference between machine learning and deep learning, that in machine learning, we manually extract features. In deep learning, if we talk about features, and with in particular CNNs, it's happening automatically. This is what we'll discover today. So when we talk about extracting features manually, this is called hand-engineered features, okay? And if you are going to do this, and you will see that it takes too much time, okay? So it's beyond just calling the SIFT like function if you are doing this. We can go in details and discuss this later, but it also can like vary, and it's not really scalable in practice. So what happens using deep learning is that we extract low features in the first layers, for example. If I want to classify, and when you talk about classification, by the way, you have for sure an input, someone, and I believe people like wearing glasses like me will understand, okay? So imagine like you don't see well, okay? Just waking in the morning, you are not wearing your glasses, and let's say your mother is coming, okay? Now, first, there is the effect of sleep. You're not that 100% awake. Second, she's far, okay? Third, like, you are trying to capture features to guess who is entering my room, okay? So, first of all, you might see something like this or something like this. So, the overall, like, thing. So, you can detect lines and edges. Next, maybe somehow some features start opening your eyes a little bit and just check some random like feature. You can see eyes, you can see hair, for example, or something like could attract your attention. And these are like mid-level features, like you are focusing with a particular detail. But if, for example, you are talking about the face, like if it's a round face long face, big hair, short hair, there is mustache, there is no mustache. Such details are high-level features, and these are related to the facial structure. Okay, so you understand as a human from our experience that if you start looking to things, it's like you are extracting features. Sometimes you go from low level to the high level, okay? So this is what a convolutional neural networks exactly does, and this is what we will see today. So it's introduced by ReLU, and you won't believe that I sent him an email to invite him as a guest speaker to our class, and for sure he's not seeing my email, but at least I tried. So I'm trying to find some guest speaker for our class. I'm doing my best, and I wish at the end you would appreciate whoever we are going to invite. This may be planned for the last class we might have. Okay, so this is the one who's introducing CNNs, and this was 1990. But what is CNNs? We're talking now about this architecture, which is different from neural networks. However, it's a type, okay, of artificial neural network. It's a particular architecture, okay, of NN. Means exactly what we learn about the propagation, cost, backpropagation. It happens within CNN, but there is a different structure, okay? So this is designed mainly to extract features. So here there is a block which is designed for feature extraction. This is what we will explore today together. These features are for sure extracted from like the input data in order to classify them given high dimensional data, okay? So what we will see now is that if I have a CNN architecture is something that looks like this, given my input, I have a feature extraction block and then a classification part. The classification part is exactly typical, like fully connected. You can see here different functions, neurons are connected to each other and so on. And at the end, there is an output layer, which is going to say this is a bicycle, this is a truck, this is a, I don't know, car or whatever, okay? And what happens now is that we are going to learn from these features that the CNN is going to extract like an engineer or a human. So how CNNs extract features? It's called convolutional. Okay. They are neural networks, they are convolutional. So saying convolutional, there is an operation in mathematics, which is the convolution operation. So they are based on the convolution operation. So there is layers that are called convolutional layers, plus ReLU for the nonlinearity. So you find convolutional layers, and between that, some pooling layers. So this is what we'll understand today. What is a convolutional layer and what is a pooling layer, okay? So again, this is maybe more clear. You can see here the fully connected part, the output, the probability values of belonging to each class, okay? So for example, here, it's a 0.7 probability, then this is 20, okay? So, and here what we have, the connection, I'm extracting some features here, then I'm taking to the next layer, reducing the size, then again extracting. You see here, I have only 3. Just focus with the dimension, okay? Okay, here is the same 3, but if you see the height and weight, they are reduced, okay? Here is larger, bigger image, okay? Bigger dimensions. And here it's less, you see? So you understand that the pooling layer, what it's doing is just reducing the size. We will see how. The convolutional layer from one image of 20, it's generating how many? 1, 2, and 3. Now, from 3, let's say, generated features from this pooling layer is generating how many? It's like how much? 1, 2, 3, 4, 5, 6, 7, 8, for example, let's say. So you can see that the convolution, it's mainly it's generating more like representations, okay? And these representations are having some dimensions that are reduced whenever you are having a pooling layer after. So this is what you need to understand until now, okay? This is how it works. Now, if your input is like the example that Jeremy was giving last time, we were talking about the classification. He's saying record of driver, for example, or for a car, automated autonomous car, for example. So if I have my data, it's like a vector. It's monodimensional data. So I need to use the convolution, which is adapted to this type of input, which is 1D convolution. If my input is like an image, and an image is 2D, okay? So the type of convolution that I use, it's the conv2D, which is 2D convolutional. And sometimes I have a tensor or 3-dimensional like input, so I must use adapted type of convolution, which is the conv3D. And in this case, I may introduce for you concepts like kernel, okay? And this is what we will see. Because when we are working with convolutions, there is a kernel, and this is the one that is going to be 1D or 2D or 3D. It's extremely simple, and this is what we will see next time to code or to write code related to CNN. So if you have 1D, you might see layers conv1D, conv1D, conv1D. If you have a 2D image classification task, you might see conv2D, conv2D, conv2D layers. So it's very simple. We'll see that. But it at the end introduces the nonlinearity. And I show you an illustration of that meme talking about the nonlinearity. If you are negative, then you stay, you don't move. Okay? This you can see with this illustration with the rectified feature map, which means if I have input features here, I apply the ReLU, any function which is like not negative, it's going to stay as it is. If any like value of a given pixel is negative, then I'm not going to give to the next layer, okay? So we apply this after every convolutional operation, like convolutional rails. It's a pixel by pixel operation that replaces all negative values by 0. So if it's 0, then you don't go, just takes value 0. If you are positive, then it stays the same value that it was in the start, okay? So this is what we can visualize here. We can see that there are black values, pixels here, they are negative. For the white pixels, they are positive. So what you see here, that only non-negative values are left, okay? So this is an illustration. Let's start now with what we say. Let's start with the example of convolution. So we said that if I have the image or the input is monodimensional, and I can reshape, by the way, my input, my image, or to 1D image, for example. So in this case, I'm going to apply a 1D filter, okay? This is the filter. And the convolution operation, how it works. So I'm going to consider this filter, okay? I'm going to multiply with respect to the order for sure, the first value from my image with the first value from my kernel filter, okay? I add to that the sum of products, okay? The multiplication of the second pixel of my image times the second value of my filter, plus I add to that the third value of my image pixel times the last value of my filter. Once I have this times this plus this times this plus this times this, I do this sum of products, I'm going to have only one result, okay? This is the convolution. So who can guess what is the value that we can put here? 0 times minus 1, it is 0. Plus 0 times 1, it is 0. So 0 plus 0, until now, there is 0. Plus 1 times minus 1, it's equal to minus 1. So 0 plus minus 1, it's equal to?
-1.
Yep, -1, okay? So what will happen next? This is, we are just doing like this with respect to first 3 pixels, but we need to go through the whole pixels, all the pixels of this image. So we need to move, okay? We move our kernel with 1 step to the right, and we do the same. What we will have here, so it is 0 times minus 1 plus 1 times 1 plus 1 times minus 1 is equal to 0. and we keep doing the same, okay, until we are done. Okay, this is the convolutional operation given like the 1D case, okay? So what we have at the end, after convolution, a vector having -1, 0, -1, -2, 1. So sometimes we have 0, sometimes we have negative values, and sometimes we have positive values. So Mr. ReLU comes in order to eliminate the negative values. It's going to be turning into 0 and keeping the 0 and positive ones the way they are, as they are, okay? So -1, is it going to go to the next level? No, so it's going to be 0. 0 is going to stay 0, then -1 is not also going to go 0, 0, 0, negative. So here is a positive value we're going to keep, and all the negative values we're going to change to 0. So is this clear? It works exactly like this. Now,
but why we eliminate the negative value?
Sorry?
Why we eliminate the negative value?
In order to add the nonlinearity. Okay, and when we the main advantage of adding the nonlinearity here is like this is input feature map, this is the rectified feature map, because this like black or negative values, they are not like in CNN. It's like this introduced that they are interested in these features. They are more representative maybe. Okay, so these are the nonlinearity. Is this clear? Okay, so but at the end, you can use or introduce a CNN and you don't use the ReLU function. So it's up to you. So we can talk about this later, because now I'm giving you a puzzle, and at the end you can create your own architecture. So what else? Now, the question is, which slide we are? Okay. Yep. I think we are here. Okay, after ReLU we had this output. And the advantage of ReLU is to add the nonlinearity. And next now what we have, sorry for this. So there is a problem now. There is a problem in this 1D kernel if I'm only considering this, okay? I started from here only, okay? And I'm ending up here. What is happening is that, what is the size of the input here? It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, the size here is 10. We have 10 values. After performing the convolution, how many values I'm having? 8. 1, 2, 3, 4, 5, 6, 7, 8. So how many values I lost? 2. I lost 2, which is important. It's not good to lose information after all. So you might ask yourself, how did I lose these 2 values? Okay, these 2 values is from here when you are doing the convolution. You are summarizing this all into 1 value. So you missed this one. And when you are starting from here, like all these 3 are becoming 1 value, okay? So what's happening? You are, let's say, eating, okay, 1 value this side, because the kernel started from here mainly. When you are putting the kernel, the middle is coming like in the second pixel. So you didn't give an importance to the first pixel, okay? So, and the same here, when you are stopping here, you didn't consider this pixel. The middle of the kernel was coming here, and like this, you lost this pixel. So what we do in this case, we do what we call the mirror effect, okay? So we add 0 in the sides. If I'm going to move now my kernel, so how is going to move? With 1 step, for example, which is called stride. So I'm going to move to this one, and I'm going to multiply this by this, plus this, this by this, plus the one in the middle. Now I'm considering it, which is the last one, by the one in the middle in the first. Plus I add this 0 just to keep conserving the value of the last one, okay? So this is the main idea. And in this case, after convolution, you are going to keep the same size as your input, okay? And again, after applying the ReLU, you are going just to eliminate the negative values, to put them 0, let's say. Okay, so this is how it works. And at the end, what we did a convolution. Okay, we can solve the problem of the size by adding like this, like zeros in the side. But there is a problem, which is here, if you focus with this one, it is your input, so we cannot discuss the input. It's like this, okay? You could add 0 here, and it's okay as well. We don't discuss this. It's just a theory, and we are applying it. But no one is asking the question, what are these weights? Okay, this is a filter, but why I'm taking the value -1, 1, -1, or -1, 1, -1 again? Why I don't take 2, 3, 4, for example? Why I don't take 1, -1, 0? Why there is an infinity of possibilities here. Why we are considering this one? Any answers for this?
Seems like it would sharpen the image in a way, because it's like increasing the contrast between values that are close together. That makes sense.
Okay, here's where you're trying to analyze the impact of this particular filter. But my question is, why this particular filter?
Yeah, I think that is my answer. Oh, sorry.
Maybe they tried a lot and this one is making the best performance.
Does it have to do with the size of the data set? Meaning if you need a sharper image, you've got a larger number, or if you need a smaller data set, you use a smaller number?
I cannot say no for all these great answers. But this is not what I'm expecting. This is what I can say. So, okay. We can imagine now a CNN, something like this, connected layers. And when we are having these connections, there are weights, okay? You remember that W's here, or the NLN side? Here for the convolution, we are understanding that somehow there is a kernel, okay? And this kernel, which is the red one here exactly, I am convolving with each pixel of the image and moving. So this kernel is same like these weights, and it is okay. I'm going to do the forward pass. I'm going to find something. Probably it's wrong. I'm going to do the backward pass. In the backward pass, these weights I'm going to update. And for these kernels, is it going to be the same forever?
The kernel of the weight where you adjust it?
Yes, if we're talking
Okay.
about adjusting something, which means that this thing has been
Correct or incorrect, either way. So you're basically like
Yeah.
lensing it in a sense.
This one has been, I'm waiting for one word. How initialized? Randomly initialized. Otherwise, what is the use of training? What is the use of optimization? What is the use of backward pass? Okay, convolution is something new, but it's a layer in the network. It's also learning in this case. Okay, in some cases, you can freeze your weights, which means you are not changing them. You fix the weights. You can freeze them so they don't get trainable, and this is possible. Okay, you can explore this in your paper. Like weights are frozen, non-trainable. But in the default architecture, these weights are randomly initialized, and they keep updating during the training process in order to extract some features, okay? And this, after ReLU, it is like a feature extracted from this input, okay? So from this input 00111, I'm having 1010. I extracted some given feature. This is what I did, okay? Is it clear for everyone, please? So this filter and these values are randomly initialized, and they, in default architecture, keep like changing with the training process until convergence. So once you find that these are not changing, it means the model is converging, okay? And this is the main like reason behind the training. So here you have W1 and W2, they are weights, okay? Is that clear? And also the B, you can have also the size of this filter. No one has said why it's 3. It could be 2, it could be 4, it could be 10. So it's called an hyperparameter, means something which is not fixed, we can't change, okay? So you learned that weights of the filter, they are random. They keep changing with the training process. However, for your kind of information, it is possible for those dealing with the deep learning project, advanced one, to fix these for a particular thing. We will discuss this later. So these weights are randomly initialized. It is for this reason that CNN are well known as black boxes. Otherwise, so whenever you talk about CNN, you will hear that it's a black box because I don't understand how it is extracting the features. It's randomly initialized something, and based on that randomness, I am having a result. So this result, which is based on randomness, it's unexplainable, okay? Probably one way to add explainability, and we can see here how it's unexplainable. So this is the paper you guys are reading, the third project. And if I'm having now a CNN, convolutional neural network, which is having 3 layers, layer 1, layer 2, and then layer 5, 5 layers, sorry. So the first layer is having this filter, okay? Which is having, you can see random values. This is why you feel some randomness here in the representation of that W's. If I have my input here, okay, which is a given bone contour, it is 1D, you can see it as a 1D like values, okay? If I am going to make the convolution of this input with this like random filter, I have this, okay? These plots I did by myself. So it's the reality. If you convert this with this, you get this, okay? You convert this in the second layer, you get the features like this with different dimensions for in the, like you have different values, but it looks like this line. Next, you convert with the third one, there is zeros, there is nothing. And the fifth one, you find the maximum value, then something like this. So these are the features that the CNN extracted. So you can see that these features, as a human, I don't understand what is the relationship between bones and this. The strong point of CNN, that is a black box, that given these representations that humans don't understand, it tells you that this is a bone with 100% accuracy, for example. Okay? They are powerful, they are great, they deal with a large data, but they are not explainable because they are based on random kernels or random filters. Now, the idea is it's possible that if we think that to use like explainable mathematical equations, like for example, I fix this kernel to something that is moving from like 0 to some maximum value and then again back, which is a Gaussian function with different sigma, I can get some results. Okay, there are features, and the convolution with this is giving me the bone each time, like getting more smooth. This is, I understand as a human, like if I have some mathematical background, I also understand this. So this is explainable. This what paper, convolutional neural network, explainable one, does, okay? So now try to go further in the equations to understand, because it's beyond the simple like Gaussian function. It's an existing descriptor of the literature that is implemented within the neural network. Okay, now we move to the 2D case. So in the case of 2D, you have an image. The image is having a set of pixels we could represent as a matrix. And here we have like, for example, these are 0 and 1 values. So it looks like something like this. And I am going to have a filter, which is having random weights like we did. And after convolution, what will happen? The size of the filter, 3 by 3. I'm going to start with the first 3 by 3 like pixels and going to like do the convolutional operation. How it's going to be performed? -1, I'm going to multiply with this one. This -1, sorry, multiplied by this like 0, okay? The last one, -1, multiplied by 1, which is given -1, -1. Then 1 by -1, -1, 0 by 1, which is 0, and so on, okay? So I do the sum of products and I'm having some value, and at the end, I keep moving my filter, okay, with a given step, or we call it stride, And at the end, I'm finding this output. Why now the question is the dimension of this image or matrix, it's 1, 2, 3, 4, 5 by 5, and the output is 3 by 3.
That's because the kernel is so much smaller and there's no padding.
There is no padding. This is the thing. There is not that zeros we were discussing, like for the mirror effect and so on. If I want the same size, I can add the padding, okay? Okay, and this is the case, okay? If I add padding, so that if my kernel is going to start, it's going to start from here, instead of starting like before from here. And like this, you are going to consider like all like these like elements, and you are going to have a final output which is having the same initial size like of the initial output. Is this clear? Online? Okay, then that's great. Now what we will do after ReLU, what we will do, we did like we ignored the negative values and we are keeping the positive ones. So a current research project is this. We just are working with Farah. She's absent today. So on like Farah is mainly working on an advanced deep learning project, and we are working on that since last year. So the idea here that we are working on is to explore the same research paper you guys are working on in the case of images. So we are working on some descriptor from images. She's also working on SIFT and trying to apply that with the deep learning model. Okay, so if anyone is having problems with SIFT, me and Farah are like having functions, implementations, and we can provide you with that. Next, now the case of 3D, it's the same concept and the same logic, and the only difference is that you are going to consider 3 channels of the image if it's RGB, for example. Okay, is that clear? So the idea is that your filter itself is going to be in the 3 dimensions, okay, and you are going to perform the same thing but given like 3 dimensions. Now let's move to the next like important type of layers, which is the pooling layers. Okay, so for pooling, what we have, it's like in general in the architecture we have convolutional layers, and after that you find the pooling layers. Okay, we will understand why, okay, later. But if you have pooling layers now, we see that it reduces the size of the image. Okay, if for example in the previous layer you are having a 4 by 4 matrix, after convolution you will have a 2 by 2 matrix. Okay, so you have different types of poolings, and like you have the max pooling, the average pooling, the mean pooling, and there are even you can introduce your customized pooling, how you want to like conserve the values, okay, at the end. So the idea is just to downsample the output of the convolutional layer by sliding the filter of some size with some stride size and calculating the maximum, minimum, or average of the input. So we will see here with an example. Here you have your input feature map. You see the size? It's huge. After pooling, what you have reduced size. You can have it like without any value, white means, or you can have it like mean. So max pooling is going to keep the max value, which is white, and the average is going to compute the average. This is why average black and white, it's gray. Okay, so here we have, for example, you are going to have like from this 4 by 4, I can like express the pooling how I can, for example, select the max, so it's 255. Okay, from this set, which is red, I will also select the max, which is 255. Okay, and the same. Okay, for example, in case, or if for example I would talk with the mean, I would select 0. I would select here the mean is the same as the max, 255. Okay, if here it's not the mean, not the max, I can also think about the average pooling. The average here is 255, and here it's also 255. But here it is in the middle, 128. Okay? So it depends if you are going to consider only the max, if you are going to consider only the mean, if you are going to sum the like and divide by 4, which is the number of pixels. So you find the average. It depends. This is another case. So if you have the majority of your like image is black and the line is in like white, the max pooling is going to give you the max, which is this case, and the average pooling, it's going to consider the average between two black pixels, 1 and 1. It's going to be 1, 255, okay? And the average between some pixels which are neighbors here, 4, which is going to be, means let's suppose 2 black and 2 white, okay? So it's going to be gray somewhere, okay? So this is the concept. This is like an illustration we have here. This is illustration is coming not from the convolutional layer, but in general we say it after convolutional layer we have the ReLU, which adds the non-linearity. So the output of the ReLU, here we are applying the pooling on, okay? So the pooling, if we use the max, we have something like this, the maximum pixel. For each like 4, let's suppose, if the size of this like kernel is 4. For each 4, I am going to consider the max value. So in the start, we can suppose that it is white, and I keep doing the same on the image. So first thing, if it's 2 by 2, what will happen? The whole size of the image is going to be divided by 2. This is why the output is having this size, okay? Divided by 4, sorry, okay? Is it clear, please? Any questions? So you can also use the sum, which is going to give you something different. So this is also an hyperparameter. You keep adjusting based on what accuracy and results you want. Okay, let's have an example. Okay, we'll just go through it very quickly. This is like the input, and this is what we want to have after the pooling layer. So you understand what is the size of your kernel here? It is the final size here. It is divided by 4, your image size. So your kernel size is what kernel size you use here, so that in the output you have like from 6 by 6 you have 3 by 3. Yeah, it's very important, but let's suppose that we are not using the stride, it's just 1. 4 by 4. Okay, let's imagine 4 by 4, which is something like this. Okay. Okay. So first you have 1, 2, and 3. Okay. But here, how much you will have? 1, 2, and 3. Okay. Or like how you think of it? No, the result. What we will mention.
Wait, what?
Hmm?
Are you asking me?
Yeah, you're answering me. Okay, the first step, okay, we are validating. I'm showing them how if I'm going to have 4, okay, it's going to be here first, my kernel.
Perfect.
And from all this, I'm going to have one result, okay? Know how, next.
Shift it to the right.
Yeah, we understand it's going to move with one step, and Ayub is right, depends on the stride. But if we keep imagining that we are using stride 1 and the size 4 by 4, these results you're going to mention here, what results are going to be? What I would write here, over here. I have, okay, for first 3, 0, 1, 2, 1, 5, 8, 9, and so on. How to select the final value from all this? You need to ask me. It depends on the type of the pooling. right? So you will say, if you will say max pooling, I'm going to choose the max between all this. If it is the mean pooling, I'm going to choose the mean between all this. If it is the average, for example, I'm going to choose the average between all this, okay? So here you need to specify, okay? Otherwise, it's clear for the size, right?
Yes.
Right? Online.
Yeah.
Yes, so like if it was max pooling, would it be 9 and then like min pooling would be 0?
Okay, let's think of it. For the max pooling, which is the maximum value here, you're right, it's 9. So here I mention 9.
Oh, it's
Okay.
not you add it all together?
The sum, yeah, or the average. You are going to sum all these and divide by, it's 16, okay? The number of
So-
pixels.
Just so I'm clear, so what you're saying is you would add all those together if it was max and get a value. But if it was,
Oh.
you know, average, you would add them all together and then divide by the total number to get the average.
We don't add them all together in all the cases. Only
Okay.
for the case of average, we add
Oh,
them
okay.
and divide by the number of pixels. This is how it works, the average. For the max, I'm only selecting the maximum value. For the mean, I'm selecting the minimum value, okay?
Mhm.
For the average, I'm computing the average value, which uses like the sum of all divided by the number, okay?
Yep.
Okay, so I think we are done for today. This is an example of pooling. Here I just wanted to show you an illustration of how it works. Like if I have a convolutional layer, I have my input, this is the car. In this convolutional layer, see how many features I'm generating or representation from this input. Now from each of these, I am like applying the ReLU function, which is I'm eliminating the negative values to add the nonlinearity, okay? And then again, I'm applying convolution. See, it's not obligatory then in CNN there is convolution and then pooling, okay? Sometimes there is convolution, then convolution, for example. After that, there is one pooling. It depends. So now the question is why we use the pooling layer?
It uses the size.
Yeah, we see that the pooling layer reduces the size, but why we reduce the size?
Is it computationally cheaper and can clear things up, like if you've got a complicated data set?
Yes and no, again. Any other suggestions or thoughts?
Can you repeat the question one more time?
So I said, we understand now the use of convolutional layer. Why there is a need sometimes to put some pooling layers? Why to apply pooling? Okay, to reduce the size, but why we reduce the size?
Overtraining?
We do that during the training for sure, but see here. Convolution. The convolution sometimes it goes to a huge number of representations. So the need for pooling is why? To always limit the features. Otherwise, they are exponential and it's going to generate huge representations. So you keep limiting. So in the next layer, even you generate more, you still have limited size, okay? Is this clear?
Mm-hmm.
So this is very tricky. Okay, now what we have. So we are done. One and then you can do it.
Can you see?